So what I'm going to do is record our Zoom sessions in case some of you get kicked out, your internet's bad, whatever. I'm going to record these and upload them to YouTube. And so if you can't join us one morning, shortly after class is over, you should be able to watch it on YouTube. All right, I think I'm ready to start. Do y'all have any questions? There were no printed notes from 3.5. Really, all there was for me to do was talk about why we need implicit differentiation sometimes. Can you tell me how you know that you're going to need implicit differentiation on a problem, even if the directions don't say so?
Y isn't on its own.
Y is not by itself, or not necessarily easy to get by itself. Now, some problems in the homework, they have you do it by implicit differentiation just to show that it works. But if you really gave me that problem on the test and just said, find the derivative, if I can get Y by itself, that's what I'm going to do. It's only when I cannot easily get Y by itself that I use implicit differentiation. Actually, there were two topics in 3.5, the implicit differentiation, and it may have been part 2 of the video that had logarithmic differentiation, when you take the log of both sides to find the derivative. So let's do some examples of implicit differentiation first. Does anyone have a specific one that you were watching on the video and just couldn't follow what was being done? Let's do examples from the video first, and then we'll do examples from problems that you've tried in the book. Does anybody have an example from the video you need to see? How did it? Abby, did you say something?
I was thinking number 32 in the video. You didn't finish it, so.
Oh, okay. That's a good good one for us to start with. Is that an x cube or an x square? That's an x cube, isn't it?
Yeah.
Now, I can tell you a common mistake in implicit differentiation. A lot of folks forget about the product rule. Now, this problem, let me just ask this first. Would it be easiest to do this problem with explicit differentiation or implicit differentiation?
Probably explicit.
Yeah, it's easy to get that y by itself. Just divide both sides by 3x cubed, and you would have simply 2 over x cubed, and that would be very easy to do. But actually easier to do explicitly than implicitly. But if we're just practicing implicit here, I'm going to go ahead and use implicit. And what I was saying about the product rule, again, if you put a dot there, you're more likely to remember to use the product rule. And anytime we differentiate a term with a y in it, it's going to have a y prime. So we would have the first factor, and you can consider the 3 as part of the first factor, or you can think of that in brackets and just keep up with the 3. Doesn't matter. I'm going to start with the first factor times the derivative of the second. What's the derivative of y?
Y prime.
Yep. First derivative of the second plus the second times the derivative of the first is 3x squared, and that finishes the product rule on the left-hand side. Another mistake that I make a lot when I'm not really paying attention is on this right-hand side, sometimes I bring down the 6 instead of saying the derivative of 6 is 0. So watch out for that. Now, these directions only said find the slope of the tangent line. If the direction said find the derivative, then I would have to solve for y prime. But do I really have to solve for y prime if all I'm wanting to do is substitute numbers and find the value of y prime? I don't. Again, if the directions say find the derivative, then I want to solve for y prime, but just find the slope or find the equation of the tangent line. I prefer to plug in numbers and then solve for y prime. So I would put the 1 in place of x, and the 2 in place of y, and that makes it very easy to solve for y prime. Is that okay, Miss Abby?
Yes.
And let me double check, find the slope at the given point. Now, actually, it did say find the derivative and then find the slope. So if this were a part and a B part on the test, I would have had to solve for y prime when it said find the derivative. But for find the slope, slope is just a number. All right. Does anybody have another question from the video? All right, somebody give me one they tried and just got stuck on.
From the homework.
Yes.
I was just worried about the notation on 59.
All right. Is that into logarithmic differentiation by that point? Ooh, that was just second derivative. Oh.
No, I just thought like the way the question was, it looked weird. So if you could like, it was just the notation like the d squared y over the dx squared. I didn't know they could switch them around like that.
When we first talked about second derivatives, I said there are a lot of different notations that you can use, and we haven't used that notation for anything. If we could solve for y prime, or excuse me, if we could solve for y and take the first derivative and then the second derivative, we would just write it as y double prime. But since we're not solving for y here, this notation makes a little bit more sense. Look back in the book where we first talked about second derivatives, and you'll see that that's one of the acceptable ways to write second derivative. It's the second derivative of y with respect to x. What bugs me about that notation is it looks like you would read it with respect to x squared. Not really. It's just with respect to x 2 times.
Okay.
So you can use y double prime. I never use that notation. It just looks difficult to me. What else do you need from the homework? Let's say up until logarithmic. Let's save that logarithmic for just a minute. But up until 69, do you have anything else? Do you remember what, talk to me about how you solve number 68. It said find the points at which the tangent line is either vertical or horizontal. How do you do that?
You see what makes the derivative 0 and undefined.
Exactly right, because where the tangent line is horizontal, the derivative would be 0, and where the tangent line is vertical, the derivative would be undefined. Good. Does anybody have another one? All right, what about that logarithmic, 69 to 80? I want to do one like 69, 71, or 73. Does anybody have one in particular of those that bothered them?
I just had trouble simplifying it all the way down, but I could do them.
Exactly, and that's why I want to tell you on the test, if we were taking tests in person, and I'm still trying to think about, I can't stand to think of giving a multiple choice calculus test. Well, I wouldn't give a multiple choice calculus test, but an online calculus test where all I see is your answer and it's either right or wrong. I don't want to do that, so I will be thinking about the test as we get closer to it. But in the problems that I chose in the MyMathLab homework, 69 through 73, similar problems, I will show that you where I would stop on those or where you can stop in the MyMathLab problem. On the test, I have in the directions, you can leave your answer as separate rational expressions. You don't have to put it all back together as a single rational expression. Let's just do 73 so I can show you where you'll stop in the MyMathLab problems. It was square root of x plus 1 in the denominator, so I'm just going to write it as x plus 1 to the 1/2. Now, could we use explicit differentiation on that?
Yes.
Absolutely. We have the y by itself, but it would be nasty to use explicit differentiation. We have the quotient rule, we have the chain rule when we have ugly to the 3/2, we have the product rule in the numerator. So it would be pretty darn ugly to do with explicit differentiation, although we could. Logarithmic differentiation allows us to use the properties of logs to make that much simpler to differentiate. Now, what you gain in ease of differentiation, you lose in difficulty of simplifying the answer. So if you had to simplify the answer all the way, I'm not sure that this would save you any time. But if the directions say you can leave your answer as separate rational expressions, then certainly we can make it much easier to differentiate with logarithmic differentiation. And that is take the log of both sides. And then use the properties of logs on the right-hand side to write that as a sum or difference of logs. So this right-hand side would be natural log of x plus 3/2 natural log of x minus 1 minus 1/2 natural log of x plus 1. I'll give you just a jiffy to write that down. And if anybody has any questions, I don't see why you did something, something, tell me. All right, when we've rewritten the right-hand side as a sum or difference of two logs, then we differentiate both sides. And remember, now we're using implicit differentiation because we don't have the y by itself. We have natural log of y. So what's the derivative of natural log of y? Anybody? What's the derivative of natural log of y?
1 over y times y prime.
Awesome. You can think of it as natural log of ugly. That's what implicit differentiation is based on. Y is some ugly that we don't really know what it is because we can't get it by itself. So when we take the derivative of natural log of ugly, we get 1 over the ugly times the derivative of the ugly. And then we've made this right-hand side really easy to differentiate. The derivative of natural log of x is 1 over x. The derivative of 3/2 natural log of x plus 1 is 3 over 2 times x minus 1. Don't forget the derivative of the x minus 1, but since the derivative of x minus 1 is just 1, we didn't have to use the chain rule on that. And then the derivative of this last term would be 1 over 2 times x plus 1. Any questions about that derivative? All right. Abby, you'll like this if you were the one that said I have trouble simplifying. All that you have to do on the problems in my math lab, and if we had a paper test, this is all I would expect you to do. Multiply both sides by y. And then put this original expression we know y to be equal to back into the derivative. So you can just leave your answer as y prime equals that original value of y times all that stuff in brackets, and you don't have to simplify the stuff in brackets. Does that make you feel better?
Sounds good.
Yeah, way better. Now, again, we made it much easier. We made the calculus much easier by using logarithmic differentiation. If we had to get that answer as a single fraction, then we've made the algebra much harder because we've got to get a common denominator, combine all those. That would be a little bit of a bear to clean up. So you can argue about how useful logarithmic differentiation is just based on how you're how you can leave your answer. If you don't have to write it as a single fraction, then using logarithmic differentiation was a good thing. But there are some other problems, 75 through 79, that logarithmic differentiation is the only way you could do it. For example, did anybody try one of those three and have trouble with it? 75, 77, 79? All right. If nobody has a preference, I'm going to eeny, meeny, miny, mo, pick 77. Let's try that one. Does the silence mean no, we got it, or no, we haven't tried it?
I got it.
Okay, cool. Cool, one person. I can't tell which person that was, but let's do this one. Even if the directions didn't say, oops, typo. Even if the directions didn't say use logarithmic differentiation, I want you to know when you would have to use it. On this problem, there wouldn't be any other way to differentiate it. You know you're going to have to use logarithmic differentiation if you have an x in the base and an x in the exponent. You couldn't just use the power rule or the chain rule because of that x in the exponent. So to use logarithmic differentiation, you take the natural log of both sides. I'm going to go ahead, when I take the natural log of the right-hand side, I'm going to go ahead and bring the exponent out front, because that's the whole purpose of using logarithmic differentiation. Now, what's wrong with what I just wrote?
You need to put x
Parentheses.
plus 1 in parentheses.
Yes, if I don't have that exponent in parentheses, then only the 1 was the exponent of the x minus 2. All right, so that's when we take the log of both sides and use the properties of logs. Haven't done any calculus yet. Now we're ready to find the derivative. So on the left-hand side, the derivative of natural log of y is what?
1 over y times y prime.
Perfect. What's it going to take to differentiate the right-hand side? You got to see that this is a product. Yep, got to see that that's a product. So you're going to have the first factor times the derivative of the second. And what's the derivative of the second?
1 over x minus 2.
Yep, times the derivative of the x minus 2, but the derivative of the x minus 2 is just 1. So we have the first factor times the derivative of the second plus the second, oops, here's the second, times the derivative of the first. What's the derivative of the first?
1.
Just 1. So I'm through with the calculus in that one step. And then I'm going to multiply both sides by y. Clean up this right-hand side a little bit if I can. That'll be x plus 1 over x minus 2 plus natural log of x minus 2 and if you don't have to get a common denominator, that's all you can do to clean up what's inside brackets. You can put this original expression for y back in the place of y. And I can't think, because I don't have the answer written down right here, I can't think if they've taken one more step or not. I can see one more step you could do, just out of curiosity. What would happen if you tried to distribute this? What would happen in the first term? If you multiplied this expression times that fraction, what would happen?
Subtract the exponents.
Yeah, you could subtract x minus 2, you could subtract that 1 from this x plus 1, and you would just be left with an x minus 2 to the x times that. But then you'd also have to multiply this times the second term, so I don't really think it would be what I would consider any simpler. Somebody who got that problem, is that how it's left in the back of the book, or have they done something else?
Yeah, that's how they did in the back of the book.
Okay, that would be absolutely fine with me. Like I said, if you did distribute this, I don't think it would be any simpler. All right, all that we need, I mean, we still have 20 minutes if anybody has other questions that you want to ask.
29 from 3.6.
29. The 16y squared minus x squared equals 16.
Wait. No, it should be h of t equals sine times arc cosine t.
And 3.6.
Okay, wait. Did you say something other than 3.5? Did you say a different section?
I said 3.6.
Oh, okay. Because not everybody has watched that video yet, can we save that one for tomorrow?
Okay.
Yeah, I'd be happy to do it, but I want to give everybody a chance at it before we try that. 3.5 today, 3.6 tomorrow, and then we'll be back on schedule, I think. So does anybody have anything else from 3.5? Everybody good? Ask all for questions. Otherwise, we're going to end the Zoom. Does anybody have any questions just about how the class is going to work? All right. This isn't quite as fun as seeing you all live, your bright smiling faces. I'd rather be in class, but like I said, on the other hand, I didn't have to brush my hair, so this isn't terrible. All right, if y'all have any questions, if you haven't finished the 3.5 homework and you go to finish it and you get stuck on a problem, just take a picture of what you've done so I don't have to, or I'm not going to work the whole problem out for you. That's what you have examples for. But if you show me what you've tried, I'll be happy to get you unstuck when you're stuck. Alrighty, I'll see y'all tomorrow morning at 8, or I'll hear y'all tomorrow morning at 8. Sound good?
I'm showing up in PJs.
What was that, Ivy?
I said I'm showing up in PJs tomorrow.
I'm already showing up in PJs.
Yeah, aren't we all?
I'm in PJs as well.
Y'all have no idea what my bed head looks like. Every hair on my head is perpendicular to my scalp.
Nice.
All right, y'all have a good day. Talk to you tomorrow.
Bye-bye.
Bye.
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 Thanks for the free math class.